Yeah, this is a talk about PHP 7 internals. So first of all, I should say the PHP 7 final release is planned for November 26th. It's planned, we're currently deciding whether we will make that date or whether it will have to be delayed by another 2 weeks. So yeah, I don't know what Anatol will decide on that matter, but anyway, PHP 7 is very close, and I think there is a lot of excitement about this release, at least a lot more than new PHP releases usually tend to get. After all, it's the first major PHP version in over a decade. It has many cool new features. I'm personally most excited about the typing improvements, so scalar types and return types. But really the main selling point of PHP 7 are the performance improvements. And here is a benchmark from the HHVM team, which compares a couple of typical PHP applications like Drupal, MediaWiki, and WordPress against different PHP runtimes. And here the blue bar is PHP 5, the green bar is PHP 7, and the yellow bar is HHVM. And what you should see here is that usually PHP 7 is something like 2 or even 3 times faster than PHP 5. And I think that's a really huge difference. And by faster, I mean not only in requests per second, which is shown here, but also in terms of response time. So usually it's 2 times more requests per second and half as large response time. And what this talk is mostly about is explaining where these performance improvements actually come from. Because yeah, they don't just fall out of the blue, so there is a lot of internal refactoring which led to these results. And before I start about the specifics of PHP, I'd like to say a few general things about how you optimize a low-level application like PHP. And it's actually in many ways similar to how you optimize a high-level application like a PHP web app. Because if you optimize a web application, the first thing you'll likely look at is inefficient I/O operations. So inefficient database queries, for example. If you optimize at the lower level, you're also looking at slow I/O operations. It's just a different kind of I/O, and that's memory accesses. So what you're mainly concerned about is optimizing memory access patterns. And from that perspective, there are basically 3 things you want to look at. The first one is reducing number of allocations. So the allocator is the piece of code which you tell, well, I need 50 bytes of memory, and the allocator responds, okay, here is an empty memory block, you can use that. And it turns out this is actually a pretty expensive operation, at least if you don't want to waste a lot of memory. And it's actually expensive to the point that PHP 5 spends about 20% of the CPU time doing nothing else but managing memory. And well, we'd much rather use that time to do something more directly useful. Now, the second thing you want to look at is reducing memory usage. And well, people commonly think that optimizing for memory usage and optimizing for performance are like totally separate goals, or even contradictory ones. So there is this term of the performance-memory trade-off where you can improve performance by increasing memory usage. And that's true. So in some cases, it's like that. But in many other cases, performance optimization and memory optimization actually go hand in hand. And the reason is that memory access has very high latency. So in the time it takes the CPU to do one access to main memory and get the result back, it can do hundreds and hundreds of operations on integers or floating point numbers. So to avoid these kinds of very expensive main memory accesses, the CPU has a caching hierarchy. So there is a small level 1 data cache in which only a little bit of commonly used data fits, but which has a short access time, something like 1 nanosecond. And then there is a level 2 cache, which is larger and has also higher access time, a level 3 cache, which is even larger and has an even higher access time. And if your data is not in one of these caches, then you have to bite the bullet and do a main memory access. And that looks like this, which is like really, really, really slow. So there is something like a factor of 100 between a level 1 data cache hit and an access to main memory. And this is the reason why optimizing for memory usage also optimizes for performance, because if you have less data, more of it fits into the CPU cache. Now, the last thing you want to look at is reduce the amount of indirection. And when I say indirection, I mean situations like these. So where you have a pointer, which points to another pointer, pointing to another pointer, pointing to another pointer, pointing to another pointer, and that one points to what you actually want to have. And well, this is bad for pretty obvious reasons. So every time you follow a pointer, you're doing a memory access, and if you're lucky, it's in the cache. If you're not lucky, it's a main memory access. And these are basically the three things we want to look at when we optimize PHP. And so now I want to apply these general ideas to PHP in particular. And well, if you talk about PHP internals, the first thing you always mention are set values. So set values represent values in PHP. So every integer, floating point number, string, array, object is a set value. And at its core, a set value only has two parts. It's a type and a value. And here on the right-hand side, you can see the in-memory representation of this structure. So it has a small type tag, the ty, and some space for a value. Now, the values can be roughly classified in two categories. So there are simple values, like null, boolean, integer, or float. These are small values which can be stored directly in here. And then there are complex values. These are things like strings, arrays, and objects. These are simply too large to store directly in a set value, and instead you have to use a separate complex data structure and only store a pointer to it. So that's like a raw value. But what you're usually interested in is storing this value in a variable, or storing it in an array index, or storing it in an object property. So you need one extra thing. So if we have a simple sample code like this, so variable a is an empty array, then this will be represented as a pointer to a set value. So each variable is a pointer to a set value. But the actually interesting case is what happens if you add an additional assignment. So we simply say b also equals a. And well, in PHP, at least by default, all assignments are by value. And not just the assignments, also if you pass an argument, that's by value. If you return a value, it's also by value. And if you take by value semantics literally, it means you have to copy the value every time you do an assignment, every time you pass an argument, every time you return a value. And that will be obviously very inefficient, because like copying an array with 1 million elements, that's like just super expensive. So what PHP does is allow sharing set values. So this is supported by introducing a reference count. This reference count just tells you how often is this value currently shared. And now we can implement this second assignment, b equals a, by adding another pointer to the same value and incrementing its reference count. So that's the basics of set values in PHP 5. In PHP 7, the fundamental idea stays the same. So you still want to support some kind of sharing mechanism. But you add one additional consideration, namely sharing an array. That makes a lot of sense, because copying an array is very, very expensive. On the other hand, sharing an integer doesn't make a lot of sense, because an integer is a very small value, and it's much cheaper to simply copy an integer than try to share it through this relatively complex heap-based mechanism. So what we do is say we move the reference count into the complex data structures, and say the complex data structures, those can be shared directly. This means that set value structure becomes much simpler, so it's now really only a type and a value and nothing else. And lastly, the set values themselves are no longer shared, so the end result is something like this. So here each variable has its own set value. Set values are always separate, but two set values can still have a shared complex data structure. And that's really the fundamental change in PHP 7. So here is a side-by-side comparison, PHP 5 on the left, PHP 7 on the right, here for a simple value. And in this case, the PHP 7 implementation is really as simple as it gets. So you have only this small, tiny data structure which holds a type and a value and nothing else. In PHP 5, on the other hand, we had to do a lot more work. So first of all, we have one level of indirection because we have a pointer involved. We had to do one allocation, so the set value had to be allocated. And we are storing a lot of information we don't really need. So it's not just the reference count, it's also the GC buffer there at the bottom. And this GC buffer is used in the cycle collector, so which collects unused cyclic references. And the thing is, well, there is no way an integer can be part of a cycle. That's simply not possible. And still we have to keep around this value. And PHP 7 just gets rid of all this overhead. Now, if we have a complex data structure, we aren't quite as efficient, so we do have to allocate the complex data structure, and we can't avoid one level of indirection. But we still save at least one level through this. And if you just sum up the sizes of these different parts, then you'll get that it's still smaller even in this case. So that's set values in general. And now I'd like to cover a few of the particular types as well. So the first one are strings. A string set value stores 2 bits of information. The first is the length of the string, and the second is a pointer to some character data. And this is basically how strings in C are normally implemented. So simply a length and a pointer to some null-terminated character data. Now in PHP 7 we changed this a little bit, so we moved to a custom string structure. So now the set value contains only a simple pointer to a custom structure, and this custom structure still has character data at the bottom. It has the length of the string, and additionally it has a hash of the string. And the hash is used, so PHP uses hash tables a lot. I'll get to that in a moment. And it makes a lot of sense for us to avoid recomputing this hash all the time. So we can simply compute this value once and reuse it later on all later occasions. Yeah, and that brings us to hash tables. So hash tables in PHP are how arrays are implemented. And the basic idea behind the hash table is that you can index memory only by integers. There is no way you can index memory by a string. So if you want to use string keys, you first have to convert them to integers, and that's what the hash function does. So here we have a string xyz, which hashes to index 1. So at index 1, we insert something we call a bucket, and this bucket simply contains the key, the array key, so here xyz, and the array value. Now we can add another key, so foo hashes to index 3, and also gets a bucket. But the case that's actually interesting is what happens if you have a collision. Because what we're essentially doing here is taking a very, very large input space. So there is practically infinite number of different strings. And we're hashing it down to a very small output space. So there are, in this example, only 4 possible output values. So there is bound to be collisions. And yeah, for example, here, key bar also hashes to index 3. What do we do now? This index is already taken. And we solve this by moving away from simple buckets to a linked list of possible buckets. So something like this. And if you now do a lookup in this structure, so say you're looking for key bar, what you do is you start off at the index 3 and look at the first bucket of this index. And then you see, okay, this is the bucket for key foo. That's not the one I want to have. So you follow the next pointer and get to the next bucket. And then again, you compare the key and see this is key bar. Yay, that's what I want to have. So that's the basic hash table idea. In PHP, there is one extra requirement. Because in PHP, arrays are ordered. So I don't know, if you're programming in Python and you iterate over a dictionary, you'll get the keys of the dictionary back in pretty much a totally random order. In PHP, if you iterate over an array, you'll get the keys back in the exact same order in which you inserted them. And in order to support this feature, PHP 5 stored an additional doubly linked list to maintain the order. So yeah, you can simply walk this list from head to tail to get the forward iteration, or from tail to head to get the backwards iteration. Okay, so that's how things are in PHP 5. In PHP 7, we still keep the basic hash table idea and the requirement of having an array order, but we try to make it a bit more efficient. And what we do is move away from these separate individual buckets towards a large array which contains all the buckets. So we have something like this. And the advantage of doing this is that we no longer have to allocate each array element individually. Instead, we have one large allocation for all array elements together. And the additional advantage of doing this is that we no longer have to store this doubly linked list, because the order of the elements is now implicitly stored in this array as well. So yeah, if you just look at it, you can walk this array from top to bottom and get a forward iteration, or from bottom to top and get the backwards iteration. So this is basically just unnecessary information now. And an additional advantage, or really sort of side effect of this change, is that we can no longer use pointers to buckets, because this array can be reallocated if you add additional elements. And if you reallocate a C-level element, then all pointers into it become invalid. So we simply can't do that anymore. And what we do instead is use indexes. So we simply say, okay, this is bucket 0, this is bucket 1, this is bucket 2. And the nice thing about this is that an index is smaller than a pointer. At least if you don't want to support arrays with more than 4 billion elements, which is sort of an unusual use case for PHP, so yeah, it's not much of a loss. Now, this new representation also has at least one disadvantage, so there is always some kind of trade-off. Namely, what happens if you try to remove an element from it? So if you remove the foo key again. In this case, we'd have to drop the bucket which is in the middle of this array. And, well, how do you drop it? I mean, to really drop it, you would have to move all elements below it one step up. And that would be a pretty expensive operation. We can't do that. What we do instead is mark it as a tombstone. So we say this element is dead. And if we now iterate over the array, go down from top to bottom, we have to skip all these tombstones. And of course, if you now create a very large array, so say you have an array with 1 million elements, and then you drop the first 900,000, then this will leave you with an array which has 900,000 tombstones. So this array, so this memory will not be reclaimed. You're getting some kind of implicit memory leak. It's a unusual situation, but it's a trade-off in this implementation. So here is a comparison table between arrays in PHP 5 and PHP 7, and I think the important numbers here are the per element numbers, because that's what measures if you have a large array. And what you can see is that in PHP 5 we have always needed 2 allocations for every element. So we have one allocation for the bucket and another one for the set value. In PHP 7 we have no allocations at all. And similarly, the size of each element goes from 112 to 36 bytes, so that's a factor of something like 3 or 4. So arrays are significantly smaller. Now, that's general array optimizations. And now I'd like to highlight one additional special optimization, namely immutable arrays. So here we have a simple sample code which creates a large outer array with 1 million elements. And each of these 1 million elements is an inner array with elements 1, 2, 3, 4, 5, 6, 7, 8. And if you now run this code on PHP 5, you'll get about 1.5 gigabytes of memory usage. So this structure is huge. And you'll get execution time more than 2 seconds. Interestingly, most of the time is spent destroying it and not creating it for whatever reason, I don't know. So in PHP 7, due to the optimizations I was just describing, the memory usage goes down to about 400 megabytes. So it's still pretty big, but a lot more efficient. And the execution time drops to 300 milliseconds. So that's maybe a factor of 6 times faster. But that's not what I want to show here. What I want to show here is what happens if you additionally enable opcache. In that case, the memory usage and the execution time drop by another factor of 10. And the reason for this is this immutable array optimization. So opcache will look for constant arrays in your source code and will immutabilize them. And this means they will be moved into shared memory, so they are shared between all PHP processes, and they do not use reference counting anymore. So basically, the difference between the last two columns is that in one case, we've been copying this array all the time, and the second case, we simply reuse the same array. Now, objects. I'll not be saying much about objects because all of these optimizations are really the same. So I've shown it once for arrays, and for objects, yeah, the ideas are similar. I just want to give you a quick overview of how they work. So what do you have to do in PHP 5 if you have an object set value and want to get a property from it? And this takes quite a number of steps, which are shown here. So the set value itself only stores a pointer to an object store bucket. This object store bucket is responsible for managing the memory of the object. And then this object store bucket has a pointer to the actual object. The actual object has another pointer to the properties table. The properties table has another pointer to the property value. So you have to go through 4 levels of indirection to actually get at something you can use. So in PHP 7, we basically dropped this, this intermediate object store bucket completely. That's just no longer necessary. And the rest is kind of merged together. So instead of having a separate object and a separate properties table, we can simply concatenate them and make them into one structure. And similarly, the property value is now directly part of the properties table and not a separately allocated value. So end result is something like this. And if you do a side-by-side comparison again, then yeah, again, you have less allocations and less memory usage. Now, last type, I'll say something about our integers. And well, there is really not much you can change about integers because yeah, only 2 properties they have is assignedness and size. And in PHP 7, we changed the size. Namely, we now support 46-bit integers on Windows. So on Unix and BSD systems, those could always use 46-bit integers. But now Windows is also a first-class-ish platform as well. So if you have a 46-bit Windows running on a 46-bit CPU, you can now also use 46-bit integers. Well, so that much for set values and types. I now switch to like completely different topic, namely the PHP compiler. So the PHP compiler is the component which turns PHP source code into instructions which are executable by our virtual machine. And this happened in 2 steps. So first is lexing or tokenization. So this step detects basic patterns in the source code. So it detects that $A is a variable, and that 42 is a number, and that echo is a reserved keyword. But it doesn't understand any of the semantics of the language. So it doesn't know that A equals 42 is actually an assignment. It only understands the parts. So in the second step, which combines parsing and compilation, we turn this token stream into executable instructions. And these instructions are then things like assign 42 to A and add A and B together and so on. Now in PHP 7, we have introduced an additional intermediary step, and that's the abstract syntax tree. And this syntax tree is something in the middle between tokens and instructions. So it captures the semantics of the language without going down to the specifics of our virtual machine. So it doesn't yet have to deal with things like instruction scheduling and allocating temporaries and so on. So in this example, the syntax tree says that you have 3 statements, and the first 2 are assignments, and the last one is an echo. And the echo works on the result of an addition, and the addition works on variables A and B. And the idea behind having this additional step, the syntax tree, is for once not mainly for performance. So performance is an aspect because by using this extra structure we can generate better instructions. But the main idea here is that we don't want to restrict the language features which we can implement by having a very, very outdated compiler pipeline. So yeah, using this maybe brings us back to, yeah, maybe 1950, but before that it was like really, really, really outdated. So I've added a couple of annotations, how you can get at these different structures from PHP. So the tokens are available as by the token get all function, which is part of all normal PHP installs. The syntax tree is not yet directly available. You need an extension for that, for example, this one. And the opcodes are available via PHP debug -p, so that also ships with PHP nowadays. And well, yeah, so that was the compiler which turns source code into instructions. And now comes the second step, the virtual machine, which actually runs the instructions. And well, there have been a couple of, a lot of different virtual machine optimizations. I'd like to mention 3 of them. So the first one is related to stack management. So here we have a very simple function which simply takes 2 arguments, adds them together and returns the result. And then we call this function with arguments 1 and 2, so we want to get back the value 3. And here are the actual opcodes for these operations. So at the top is the call opcodes, and the bottom is the body of the function. And now I'd like to walk you through what happens at runtime if you execute these. So for that you have to look at the virtual machine stack. That's the place where all the execution state is managed. And the first thing that happens is that you send the arguments. This means that the arguments are pushed onto the virtual machine stack. Then next step is the do fcall instruction, which pushes a call frame onto the stack. And this call frame has 3 parts. So in the middle there is an execute data. That's just general information about the function you're currently calling. Then below it are the slots for variables. So variables like A and B in this example. And above the execute data, you have slots for temporary variables. So this ~0 is a temporary. And the first thing we now have to do when we actually enter the function is receive the arguments. And what this does is copy them from the argument stack into the variable slots. So we have now duplicated this information. And then after we have received the arguments, we can simply add them together and get a result. Now, the main thing I want to show here is that the arguments appear on the stack twice. So we have them once in the argument stack and again in the variable slots. And in PHP 7, we'd like to improve on that and only have the arguments once. So in PHP 7, the instructions are very similar. The only difference is that we now start with an init fcall, which pushes the call frame right away. This call frame is still the same as previously, only the order changed a little bit. So temporaries are now at the bottom, not at the top. And now if we send the arguments to the function, so we do send val 1 and 2, these arguments will be placed directly in the correct variable slots. And this means that when we actually call the function, we can skip over the receive instructions and can go directly to the addition. So yeah, this saves some memory on the virtual machine stack, and it also means that we can save a couple of instructions at the start of every function call. However, this change is not fully transparent to user PHP code. So usually it doesn't matter, but there are a couple of cases where this will actually influence how PHP code behaves. And the case when this happens if you assign to an argument in the function. So say if you, before the return statement there, you add something like a equals 42. So you overwrite the argument. In this case, the value 42 will be changed in the variable slot. And we will no longer know what the original argument was. So we no longer know that originally the value 1 was passed, and we only overwrote it later. And well, usually that makes no difference. But if you're using something like func_get_args, you will now get the changed arguments instead of the original ones. And for some pieces of software, that's actually a problem. So if you're using some kind of old version of Doctrine, then you may run into this issue. So that was one virtual machine optimization. There are a couple of other ones. Another one I would like to highlight are specialized functions for, specialized opcodes for a couple of commonly used internal functions. So functions like strlen, isInt, isBool, whatever, define, call userfunc, call userfunc array. These now have custom instructions in the virtual machine. So instead of emitting a function call to an internal function, which is a relatively expensive operation, we now have specialized opcodes which can compute the value directly. And there is only one problem with this. Okay. Namely that it doesn't work in global, that it only works in global scope, or if you're using fully qualified calls. And the reason is if you have code like this, so you're in a namespace and you call the strlen function. We don't know whether this is the global strlen function or if it's a namespace local override. And yeah, so we don't know that at compile time. We only know it at runtime, and so we can't optimize it. Now, you can fix this by adding another backslash in front. So if you're using a fully qualified name, we do know that this is the global strlen function, and it can be optimized. And yeah, well, this actually shows that the PHP application that we usually use to measure performance improvements in PHP is WordPress. And WordPress is, yeah, kind of maybe not the most modern kind of PHP code. It definitely doesn't use namespaces, so this optimization will work great there. But it will not apply for, I don't know, a Symfony project or really anything any modern library that uses namespaces. Okay, so last optimization I'd like to mention are global registers in the virtual machine. So there are two pieces of information which the virtual machine uses all the time. And this is the execute data, which is the call frame, and the opline, which is the current instruction. And what we can now do is add a couple of compiler annotations. And what these annotations mean is that the registers 14 and 15, so CPU level registers, are now reserved. They're reserved to store these 2 bits of information and cannot be used for anything else. And the purpose of this kind of reservation is that we no longer have to reload their values from different structures, so like the execute globals. And it also means that we do not have to save and restore these 2 values every time we do a function call. So on a normal Intel CPU, which your servers are probably using, this optimization gives an improvement of something like 2%. But on a couple of other architectures, I've heard that you're getting much larger differences. So on something like PowerPC, this very small change actually led to an improvement of something like 20%. Because these architectures have a lot more registers, so it doesn't. So it's much cheaper to reserve specific registers. And yeah, that's actually, so normally we are very happy if we optimize something and get something like a 0.5% improvement on real code. And it's like really amazing if you do an optimization and get a 20% improvement. But anyway, that's really all I want to cover today. So yeah, thanks for the attention. I have here a joined in link for feedback, and yeah, thanks.